Friends, I welcome you again for this lecture on NPTEL course for earthquake resistant design of foundations. And today we are going to talk about a new module. So far we have already covered introductions, shallow foundations, then major topic pile foundations. Today we are going to talk about well foundations. The well, that is the fourth module here, and you may be aware that some of you that well foundations are mostly used for as a foundation of the bridges, particularly in our country. So, this topic well foundations we are going to cover under these subheads, or you can say the chapters under this module 4. We are going to talk first introduction, then lateral stability of well foundations, construction and sinking of well, and numerical problems. Now, we are going to talk introduction now, and then we will talk about lateral stability. So, let us talk today the first chapter, that is where the wells are used. So, under the introduction in this chapter we are going to cover these issues: usage of wells, types of wells or caissons, components of a well foundation, shapes of wells and depth of well foundations, and finally forces acting on well foundation. So, beginning, and this is like the things which is mostly also covered at the undergraduate level, but it is important to review before we talk about anything like the seismic forces or earthquake resistant design, that what are the different issues related to wells, including their types, components, shapes and depth. So, first one is usage of wells. So, when we talk about that, as we discussed earlier also, that pile foundation and well foundations comes under the category of deep foundations, and these foundations provide a solid and massive foundation for heavy loads and useful in situations where the loads to be transferred to the soil stratum deep below. So, two issues with the well. One issue is that load which is need to be transferred is heavy, and they need to be transferred to be deep stratum. And the difference with the pile foundation is the wells is basically you can say the large diameter piles. So, other way many of the things are common, being the deep foundations, both are pile foundations and well foundations being the deep foundations. However, the diameter of the wells is quite large compared to piles, that is there. As a result, they are able to provide a solid and massive foundations for heavy loads, including the loads of the bridges. In the case of bridge foundations, wells have been widely used in our country as a foundation for bridge piers and abutments, and they are equally popular in western countries also. Well are also useful in situations when the uplift are large, as in case of transmission line towers. That means when there are due to the wind forces or some other reason, if there could be uprooting of the towers, and then it can generate uplift, in that case also well will be useful. Being a massive substructure, it is monolithic and relatively rigid in its structural behavior. So, you will see that when we do the analysis of the wells, that most of the theories assumed in some situation that well is behaving like a rigid that block, or you can say rigid structure. So, with this background of usage, let us talk about types of wells or caissons. When we talk about that, there may be many types of categories, but most of the wells can be grouped into three categories. One is called open caisson, then you have box caisson and pneumatic caissons. So, first of all, wells itself is also called caissons, which is coming from the French word. So, we can say open caisson or open well. Then we have box caisson, pneumatic caissons. Open caisson, as in the first shown in the first figure, it is open from the top as well as bottom, that is why name is given. Box caisson is the closed from the bottom, and it looks like a box type of structure. So, the name itself says box caissons. Then the third one, pneumatic caissons are pneumatic, that means related to air. So, based on this system, so you have the air locks, air shafts and all these things, then that kind of caissons are called pneumatic caissons. We are going to talk about these three types of valves in detail. The first one is open caisson. The top and bottom of the caisson is open during construction. It may be of any shape in plan, circular, rectangular, oblong etc. So, when we talk about open caisson, it could be cross section, might be most of the wells have the circular cross sections, but there could be situation where it could be rectangular or it could be elliptical or oblong, that means one longer in one direction and smaller in other directions. Open caisson have a cutting edge which is fabricated at the site, and the first segment of the site shaft is built on it. So, what is done, if you see here in this figure, so what you could see, this is the cutting edge. So, both of this is what we can say cutting edge for the open casing, cutting edge. So, this will actually, if I treat this, let us say this is a ground level, this is ground surface, and what happens then when you sink down, then it will start cutting the soil or the earth and then will proceed down. So, it is not that it will go in one go, rather than you first put it down and then push it down, and then the sand inside this valve is called, what is the one term is called dredging. If you would have dredging, that means it is taking out. So, sand is dredged and it has a cutting edge which is at the end is built on it. The soil inside the shaft is dredged by suitable means and another segment is added to it. The process of sinking is continued thus till it reaches the required depth, and then what is done, the bottom is sealed with concrete and shaft is filled with sand. So, first thing is that it is open from the both bottom as well as top. Later on, when it reaches to the desired depth, then bottom is closed with, it is called plug, and this bottom plug is normally of concrete. So, you have the concrete plug, and once it is sealed, then it will be that from that no other material can go down there or sink. And then this is as you may be aware that when the sand is dredged, it is not necessary to fill it again or from other material. So, it could be hollow, and most of the wells they have the hollow. So, the sand is taken out and this will be hollow section. So, this is there. So, what you have here, the bottom is sealed, concrete shaft is filled with and then it could be there are two choices. One is that it could be kept hollow, or otherwise it can be filled with some other material or the sand dredged some other. So, what are the advantages of this? It can be constructed up to any depth and economical, while the disadvantage, the progress of construction in boulder deposit is very slow. If you have the hard rock strata, then it will be difficult to cut, and then this is slow. The concrete seal placed underwater is not effective, and also the bottom cannot be inspected. So, these are the issues with open caissons. Then we have the box caissons, which is also called floating caissons, and these caissons are open at the top and close at the bottom, first casted on the land and then toe the site where it is sunk on the previously leveled foundation base. This is used where the loads are not very heavy and bearing stratum is available at a shallow depth. So, what is done here? Compared to compared to this open caisson is casted at the site itself, but box caisson is casted at somewhere else and then it is towed to the site. So, as a result, the you cannot have the height of this caissons, or it can be for a limit, they can be used up to a limited shallow depth, that is up to a limited depth only. That is one disadvantage from this box caisson, and another thing, you require a bearing stratum. Okay. So, disadvantage written here again. Foundation bed has to be prepared in advance, and bearing capacity of the base has to be properly accessed. Also, care has to be taken to protect the foundation from scouring action. So, this was the story about box caisson. The third one, which is pneumatic caissons, and it is better than the first one, open caisson as well as box caissons, because it is on the principle of the pneumatic air pressure. A pneumatic caisson has a working chamber at the bottom of the caisson which is kept dry by forcing out water under pressure, thus permitting excavation under dry conditions. So, what is done here? In case of pneumatic caissons, a working chamber is prepared, which is you can see here. This is working chamber here where you have this air shaft. So, what is done using this air shaft? Then you have the air lock. So, the water like that the air is pushed inside and the water is taken out. So, when the water comes out of this well, that means the chamber inside this dry and one can work in dry condition in a better position rather than working in the wet condition as for the other wells. So, this will act like a so this will work like a what we say this cofferdam also. Air locks are provided at the top. The caisson gradually sinks as excavation is made. On reaching the final depth, the working chamber is filled with concrete. So, once it is filled, then then it is reached to the final depth, then this can be filled with the concrete. So, this is the advantage of pneumatic caissons, better control in sinking and supervision. Also, the bottom of the chamber can be sealed effectively with concrete as it is placed under dry condition. Further obstruction during sinking, for example, boulders etc. can be removed quite easily. So, that is the advantages of the pneumatic caissons, but there are disadvantages also. Very high cost and the limit on the depth of penetration below water level of about 35 meter, a pressure of about 3.5 kilograms per centimeter square. So, it is high pressure. Higher pressure are beyond the endurance limit of the human body. So, it is difficult that we can increase beyond this pressure. And another biggest disadvantage of the pneumatic wells are that is the costly, and naturally their construction installation require this technical know-how. It is not simple like you have open caisson. So, it requires some skilled and that may not be always available at all the sites. So, this was about types of well foundation. Now, we come to the next point, that is component of a well foundation. When we talk about components of a well foundation, what has given here? You could see on the right hand side of this slide a picture is given. So, let us before we discuss one of each of the component, what you have the girder of a bridge which is transferring the load through bearing to the pier cap and finally to pier. What will done? Pier will transfer the load to the well cap. So, this like say well foundation are going to start from this point, below this point. So, the well cap is the top base of the pier and above the well foundation. So, the well cap is a connection between this. Then well steining, you could see there is one arrow, it is the main body of the well. The well steining here, and this is like that you have a, if you have a circular well, then you have a cylinder which is made of concrete. So, the well stain is normally made of RCC, reinforced cement concrete. Okay. Then you have this reinforcement, vertical reinforcement, horizontal reinforcement as shown in the figure. Then bottom plug is there, top plug is there, plugs are the same similar which we have discussed earlier for let us say box caisson as well as open caissons. So, these are the made of concrete, they are used to seal the bottom as well as top. Then in between you have the sand and naturally this sand portion is quite big compared to top plug and bottom plug. So, this figure you can say this is not to the scale, and this is plan what you could see here, this is plan of the wall. So, section what you have here, here you have well curve and cutting edge. So, cutting edge is here. So, what is done that this try to keep cutting like this cutting edge will be used to sink the well inside the soil, and then you have curve, and let us discuss one by one each component. The various components of a well foundations are briefly described here. So, you have well cap, and this is as discussed RCC slab laid at the top of the well steining and is usually cast monolithically with the steining. So, the well cap and steining which is main body of the well, they are casted together. It transmits the forces from pier to the body of well. The dimension of the well cap should be sufficient to accommodate the pier. Naturally, because pier will transfer the load to the well cap. So, the plant dimension of the well cap should be sufficiently larger than the base of the pier. So, you could see here. So, you should have enough setback, so that your pier can sit on the well cap, and the recommended minimum thickness is 0.75 meter. So, thickness of well cap is minimum is 0.75 meter. So, this is thickness means 75 centimeter is the minimum thickness required for the well cap irrespective of the load or you have. So, that can be increased when depending on the load condition other things. After well cap, next is staining, which is also called well staining, and well staining is already shown. This is the main body of the valve, the wall of the valve which transfer the load to the subsoil. So, what it will done that pier will transfer the load to the well cap will transfer to the well staining, and finally well staining will transfer the load coming from the superstructure to the soil. So, you could see that this is like you know the well staining, you can say in fact this is well itself is well staining. That means the main body, the cylinder which is used to transfer the load from well cap to the down soil, that itself is a well staining. So, well staining is shown here, and then this is also act as a cofferdam during sinking and provides the weight for sinking. The thickness should be sufficient so to overcome skin friction developed during sinking by its own weight. So, what will happen when you sink the well inside the soil, and due to heavy well itself, it should not happen that the side wall or the well staining get collapsed. So, this should be sufficient to overcome skin friction which will develop, and the minimum reinforcement in the well staining should be 5 to 6 kilogram per meter cube, of which 75% is to be provided as vertical and 25% as the lateral ties or hoop rings. So, what you have the reinforcement in the vertical direction, and then whatever reinforcement you need to connect, you know that what is like hooks using the rings and the lateral ties. So, so the total reinforcement 75% is in vertical direction and 25% goes to the lateral ties. The minimum thickness of the well staining is 0.45 meter or 1/8 of the external diameter of the well for big brick masonry, and 1/10 for well with cement concrete. So, all three out of these three values, whichever is higher, that should be used. So, minimum recommended is in any case is 0.45 meter, that means staining thickness should be minimum 45 centimeter, while the well cap thickness minimum was 75 centimeter. Then 1/8 of the external diameter of well for brick masonry, and for cement concrete if you have brick masonry, then you require the higher thickness of the well staining, otherwise 1/10 could be okay for cement concrete. So, this was the main body of the well staining. Then well curve which is used for cutting. So, you could see here just this is cutting edge here and well curve is here. So, you have well curve in the shown with this arrow. So, that is used for curving, and then you know like pushing soil inside and then going ahead. So, this well curve, the well curve support the staining. The curve should be slightly projected from the staining to reduce the skin friction during sinking of well. It is made of RCC with steel cutting edge. The minimum reinforcement to be provided is 72 kg per cubic meter. So, you could see compared to staining, it is highly reinforced. Here the figure was 5 to 6, but now it is jumped to 72. The inner portion of the staining should have a slope of 2 to 1, that is 2 vertical to 1 horizontal. So, what you have here? So, here this is the inner portion. So, we are talking about this slope. So, this slope should be 2 to 1, where 1 is vertical and horizontal. So, you should have more vertical distance than horizontal, that means it is will be the angle which will make the horizontal will be less than or it will make with the vertical will be almost it is less than 45 degree. So, what you have the well curve, you could see the well curve is coming out, there is some projection, right, this there is some projection, this projection both sides on the well curve. So, well curve have higher thickness compared to your well staining, and it is highly reinforced because this is the well curve which will go first down, and on the top of that well staining is transfer its loads to well curve, and finally well curve will transfer its loads to the soil. The next cutting edge is nothing but just below the at the end point of the well curve. So, this is the cutting edge is either projected below the curve as a sharp edge or can also have flat bottom. The projected edge is likely to be damaged in strata of gravels and boulders. In such soil the flat bottom cutting edge is provided. So, wherever this this curve is ending, then your cutting edge is started. Then you have the bottom plug. Top plug and bottom plugs, they are normally made of concrete and made bowl shape in order to have an arch action. The bottom plug transmits load to the soil below. When sunk to its final depth, bottom part is concreted to seal the bottom completely. The thickness varies from half to full inside diameter of well, so as to be able to resist uplift forces. Now, the issue is this: what should be the thickness of the bottom plug? So, you have, so this is like you have this bottom plug, and bottom plug should be thick. How thick should be? So, it could be half or to full inside diameter. So, whatever inside diameter of the well you have, so at least half of that diameter, that is the radius of the well, or more than that should be there. So, it is able to resist the uplift forces. Then sand filling. After concreting the bottom plug, the sand is filled above the bottom plug and below top plug. Sand filling provides stability of well, reduce tensile stresses produced by bending moment, and distribute the load of superstructure onto the bottom plug. Sand filling relieves load to staining to some extent. So, here we need to understand that you have pier will transfer the load to well cap will transfer load to the well staining. Most of the load is transferred to the soil through well stoning, but some of the load is directly shared by the soil, because sand is filled inside this. So, well cap also transfer directly to the soil some load, and it will reduce or relieve the load coming on staining. But still in case of well foundation, major load will be carried by well staining, not directly by the sand or soil filled inside this well. Okay. So, this is the case there. Then after this you have top plug. This is a plug at the top of the well below the well cap. This helps transferring the load through the granular material into the staining. So, this we already discussed. Now, let us talk about different shapes of wells. So, there are, depending on the requirement, depending on the situation, the different shapes of the wells are available, and the most commonly adopted section, most commonly or most popular is circular section. And the simple reason is this is the least perimeter for given area of the base. So, if you have a circle, you know that if you have the same circle and square, the perimeter for the same area, perimeter of the square will be more, while circle will be less. So, let us, this may be, or you can, if you have different area, then also it is like this. So, this is let us say square, and then you have the same circle. So, circle normally if you want to keep the same that area, so the diameter of the circle will be higher than the B, because if you keep this is the D, so D will be higher than B. Actually, you can work out that pi by 4 D square, you have the area is equal to B square. So, you get here, if you work on the D, you get simply D will come out B divided by pi by 4. So, the diameter this area pi by 4 D square, this is all right, and then you have, so sorry, it will be 4 over pi, it will be opposite, that is why this I was wondering what happened, it will be 4 over pi. So, when you work, so let me cancel this, D comes out to be 4 divided by pi into B, because pi is 3.14. So, D is going to be greater than B for the same area, and for the same area, as a result, if you have this you are going to get the higher perimeter for the square section compared to circular section. So, you have this the distance of the cutting edge from the rays. So, what you have, this has the least perimeter for a given area of the base, and hence is the ideal section in terms of the effort needed during shaking. Also, as the distance of the cutting edge from the raise hole is equal, sinking is more uniform. However, there are disadvantages lies in accommodating a large oblong pier, which would require a large diameter well. In the case of large oblong piers, 2 or 3 independent circular wells which are placed very close to each other with a common well cap can be used. A combination of independent wells is easy to handle, but they have a tendency to tilt towards each other during sinking. So, circular is the first choice, but what happens, suppose if you have a pier which have direction in one direction more oblong pier, in that case you can circular is not going to be economical. Then you need to select either 2 circular sections and then connecting with that with some neck, which we are going to discuss. So, let me show you some figure first. These are the different shapes of wells, though it does not look like first one is circular, though it is little looking elliptical. So, this is circle, then you have double D well, then you have dumbbell, and then you have broad neck twin well with circular draise holes, then you have octagonal with circular draise holes, multiple draise hole well. So, these are the different, like that first one which is circular, this is the most popular, and if this does not work, then people go for dumbbell. Next one, that they have 2D or 2 circles, then they are connected, or maybe the last one, this is where you have the circular and they are connected with broad neck twin well. So, this was the case here. Tied wells of different shapes are preferred in order to avoid relative tilt between wells. So, rather than keeping 2 wells separately and they are not tied to each other, then what happens, they may have tendency, if the distance between them is not very large, then they can tilt, and tilting, if one well is tilting, another well is tilting, and then they this may be a dangerous effect. So, as a result, to avoid the tilting, either the distance between the wells should be enough large, or if they are nearby, then it is better to connect them using some neck, which is shown in the last figure, like here broad necked twin well with circular draise holes. Okay. So, this was about the different shapes of the wells, and then after that we discuss there is a code IS 3955 1967 that was published, which is on well foundation, and this code on well foundation, that is for design and construction of well foundation, has laid down the some requirements for the horizontal cross section of the well, and these requirements are listed here, the codal requirements. The first one, the draise hole should be large enough to permit draising, okay, that is the one thing. So, you should have the size of the draise hole should be enough. The staining thickness should be sufficient to transmit the load and also provide necessary weight for sinking and adequate strength against forces acting on the staining, both during sinking of wells as well as its service. So, staining thickness should be sufficient enough. Then it should accommodate the base of the structure and not cause undue obstruction to the flow of water. So, idea behind that wells is that and then when you provide the well staining and all the things, that is, it is able to accommodate the base of the structure, and that means its size should be enough that whenever you are transferring the load through pier, so it have the enough size to accommodate the pier, but at the same time it should not be so big that it is causing the obstruction to the water flowing down there. So, these are the requirements. The overall size should be sufficient to transmit the load to the soil. It should allow for the permissible tilt and shift of the well. Whatever the tilt and shift which is permissible, it should be able to allow. Then further, the code recommends that any shape that fulfills the above requirements may be adopted. Also, when a group of wells sunk, the minimum spacing between them depends on the depth of the well. So, when you are sinking more than one well together, then there should be some minimum spacing between 2 wells, and for general guidelines and design, a spacing of about 1 meter may be used. So, at least spacing between 2 wells should be, minimum spacing is recommended is 1 meter. So, that should be 1 meter apart, and then this should be kind of a clear spacing between the 2 wells. Then continue with this. The next issue is related to depth of a well foundation, and this is most important for the analysis and design of the wells. And when we talk about depth of foundations, well foundation, there are 2 important requirements which influence the depth of well foundations are listed here. First requirement is minimum grip length below the scour depth. So, below the score depth, at least you need to provide some minimum grip length, which we are going to talk in detail. Then base pressure to be within permissible limit. So, whatever pressure is coming on the base, that should not exceed simply the safe bearing capacity of the soil. So, that is the general principle, and that need to be followed. Now, for natural streams which is flowing through alluvial bed, the normal depth of score D, which is in meter, below high flood level, which is denoted as HFL, for regime conditions in a stable channel is given by the following equations. And the equation listed is here, gives you the depth of score depth, that is D. This is not the depth of well foundation, you are finding depth of score, and the depth of score depends on two factors. One is the flow Q, that is which is in design discharge in Qmac. So, that is the one factor, and the second factor, when this water is passing through some granular soils or some kind of soil. So, what are the sizes of the particles through which it is passing? So, that can be determined based on the this factor F governs on these characteristic of the soil, where F is called Lasse's silt factor as given here, and then simply F equal to 1.76 root m. So, this is the way how you can find the value of F here, where m is nothing but mean size of particle in millimeter. So, when you put the value of m in millimeter, then you can get the value of F, and this is called value silt factor, Lasse's silt factor. The values of silt factor F as recommended by IS code is given in next slide. So, what are the values? If you see, these are the values which is recommended by the code. So, you have the type of bed soil, and then you have size of particle in millimeter. So, you have coarse silt, fine sand, medium sand, coarse sand, gravel, and finally boulders. So, naturally when you go towards the boulders, then the value of m is going to increase, m is going to be continuously increase as listed in this here also. So, this m is in millimeter. So, what you have, you can treat this basically this column as m only. So, for example, this gives you the value of m. So, m equal to 0.04, 0.08. So, it becomes double, and then root of that you find out that what is called Lasse's silt factor. So, as you can see, the value of m is increasing, the value of f is also increasing, which was expected from this formula. Okay. So, either you can use this formula 1.76 root m number 1, or you can use this table to generate the value of m and later on phi. So, this was there. Now, let us talk about for maximum recommendation for maximum score depth. What are the recommendations? Score depth, of course, you can find using this relation here in a stable channel. So, but this will give you kind of a minimum value, and for design or analysis we need to go beyond that. And as said, below the score depth there should be some grip length, to accommodate that grip length, and what has been recommended that these are the maximum depth of score, and this is in stress reach, it should be 1.27 times of D. At a moderate band it is 1.5 times, at a severe band 1.75, and at a right angle band 2, at upstream noses of guide banks 2.75, in severe swirls. So, you have this one, that 2.5. So, this is the case here, that means depending on your situation, then you can find the value of maximum depth of score, which can be obtained depending on the value of D. The grip length is taken as 1/3 of the maximum score depth, which we have already discussed. Thus, as per IS this code, the depth of foundation should not be less than 1.33 times the deepest score below HFL. So, this is the case here. So, the depth of foundation should be at least 33 times the deepest score below HFL. The depth below the score line should in no case be less than 2 meter for piers and abutments with arches and 1.2 meter for piers and abutments supporting other types of structures. So, now the issue is this one, depth below the score, this which is basically grip length. So, grip length is normally 1/3 of the depth of the valve, but it is not necessary. But what is the minimum guideline said that this grip length should be minimum 2 meter for piers and abutments with the arches. Otherwise, this can be done 1.2 meter for piers and abutments supporting other types of structure. So, depending on which category you are falling, then you can select either 1.2 or 2 meter after this. Then next is this maximum base pressure should be less than the allowable bearing pressure. This is important from the consideration of safety of wall. For wells in cohesionless soils, the allowable bearing pressure can be estimated from the standard penetration test data, which is given in this relation. So, you can find the value of 1 minute, yeah, here. So, you have this value, this as per the allowable bearing pressure is obtained from this, and this allowable bearing pressure, where Q is allowable bearing pressure in kilogram force per meter square. So, this allowable bearing pressure is basically only on the value of N, which is corrected SPT value. So, corrected SPT value you can have this one. This relation will be gives you the value of QA, allowable bearing pressure, where N is corrected SPT N value. That means, based on N values which is easily available, you can find the allowable pressure, where B is the smaller dimension of section in meter. So, suppose if you have circular dimension, then B is diameter, but if you have elliptical, then smaller will be B, and D is the depth of foundation below score level in meter, which we will discuss also in detail later. For wells in cohesive soils, consolidation shear strength parameters should be obtained from tests on undisturbed soil samples. The allowable bearing pressure is determined with the help of these parameters. In case of rock, the allowable bearing pressure is estimated from the crushing strength of rock, which can be determined from the test on rock mass. So, this way you can find first of all allowable bearing pressure and grip length, and the next one is that forces acting on wells. So, we will talk about these things in the next lecture. Okay. Thank you very much, and I will have this forces acting on wells and other things in the next lecture. Thanks.